Hello, my name is Carolyn O'Day, and I am a neonatologist at the Children's Hospital at Dartmouth-Hitchcock Medical Center. In this program, we will discuss ventilation and perfusion. Module 1, Ventilation Equations. In this module, we will discuss the equations related to ventilation and perfusion. In this module, we will focus on learning the determinants of gas exchange and understanding the concepts of anatomic and physiologic dead space. Let's start the discussion of ventilation using a healthy term newborn to illustrate a few points. This healthy 3-kilogram infant has a tidal volume of 5 milliliters per kilogram and a respiratory rate of 30 beats per minute. Doing a few quick calculations, you would find that the total lung volume leaving the lung each minute is 3 kilograms multiplied by 5 milliliters per kilogram multiplied by 30 beats per minute, which equals 450 milliliters per minute. This volume is the total ventilation. It is important to understand, however, that not all the air that is inhaled reaches the alveolar gas compartment where gas exchange occurs. Of the tidal volume this infant inhales each breath, calculated at 15 mLs, about 1/3 remains in the anatomic dead space, or 5 mLs in this example. Thus, the volume of fresh gas entering the respiratory zone is the tidal volume minus the anatomic dead space volume times the respiratory rate. This is called the alveolar ventilation. Alveolar ventilation is important because it represents the amount of inspired air available for gas exchange. Alveolar ventilation is determined by the tidal volume, the dead space, and the respiratory rate. It is relatively easy to measure the total ventilation, which is tidal volume times the respiratory rate. Alveolar ventilation is more difficult to determine because dead space is not easy to measure. Once the dead space volume is determined, alveolar ventilation can be calculated by determining the difference between the tidal volume and dead space volume and multiplying that number by the respiratory rate. In order to better understand the alveolar ventilation equation, it is important to discuss dead space. Dead space refers to areas with high ventilation perfusion ratios. There are 3 types of dead space. First, anatomic dead space are those parts of the lung areas that are not involved in gas exchange, such as conducting airways. The amount of anatomic dead space is most commonly affected by bronchoconstriction, which will decrease the total anatomic dead space, or bronchodilation, which will increase the total anatomic dead space. Alveolar dead space refers to the alveoli that are not involved in gas exchange because of shunting or due to abnormal pulmonary vasculature. Again, your ventilation perfusion ratio is greater than 1. Physiologic dead space is the sum of anatomic dead space and alveolar dead space and can be thought of as unused or wasted ventilation. It is important to recognize that physiologic dead space is always greater than anatomic dead space, and that when we refer to dead space volume in the alveolar ventilation equations, we are referring to the physiologic dead space volume. Again, the sum of anatomic and alveolar dead space. The Bohr equation is a means of calculating physiologic dead space. It is based on the concept that any measured carbon dioxide in mixed expired gas came from alveoli that are involved in both ventilation and perfusion due to the minimal amount of carbon dioxide in inspired air. The goal is to calculate the total volume of carbon dioxide in expired air, which is equal to the sum of the volume of carbon dioxide from dead space plus the volume of carbon dioxide from alveoli involved in gas exchange. The derivation from the Bohr equation to the equation for dead space volume, shown on the next slide, can be found in a variety of textbooks if you are interested in it. It is relatively easy to measure the total ventilation, which is tidal volume times the respiratory rate. Alveolar ventilation is more difficult to determine because dead space is not easy to measure. Once the dead space volume is determined, alveolar ventilation can be calculated by determining the difference between the tidal volume and dead space volume and multiplying that number by the respiratory rate. The equation shown here is how you can attempt to measure the dead space volume. Dead space volume equals the tidal volume multiplied by the alveolar carbon dioxide minus the expired carbon dioxide divided by alveolar carbon dioxide. We have now discussed two important respiratory equations and have the tools to calculate alveolar ventilation. In this module, we discuss the three components of ventilation: respiratory rate, dead space volume, and tidal volume. I showed you how to calculate the dead space volume and the alveolar ventilation volume. This concludes Module 1. Thank you for your attention.
We would like to acknowledge the American Academy of Pediatrics, the Organization of Neonatology Training Program Directors, Neo Reviews, and Abbott Nutrition for their support of this educational program. This concludes this module.